Welcome to Maths with Bob. Today we're looking at mechanics, circular motion in the horizontal plane, and in particular the conical pendulum. Now obviously it involves cones, conical pendulum. We'll just try and see if this pen will work. Yeah, okay, alright, so there is, in fact, you can see here a particle P which is suspended from a light inextensible string or rod, I guess you could say, it depends, from the apex of the cone up here at A. There is a little angle here, theta, you can see there. That's a semi-vertical angle, or half the vertical angle of at the apex. Okay, the few things, there is a length L, a height H, and a radius R. Okay, so these are the important things about the conical pendulum. Now the particle P is actually going in circular, the particle P here is going in circular motion, and we'll just have a quick look at what that looks like. Okay, here we have GeoGebra, and I'll see if I can get the particle to start to rotate here. Okay, looking at the different views, you can see obviously you can look at this conical pendulum from lots of different angles, but here we go. Okay, so the particle P now is rotating around the axis of the cone. You can see radius R, P, the semi-vertical angle theta, length L for the light inextensible string. Okay, so basically it's just traveling in a circle. Okay, you can see here. Okay, alright, so let's have a look at the forces now. Okay, well here we are. We have, I'll just put the forces in onto the conical pendulum. You can see looking at different views, but basically we've got the weight mg acting downwards. We've got the tension in the light inextensible string, if you want to think of it like that. It has a component T cos theta. This is obviously vertically, and those two forces T cos theta and mg are balanced. Okay, so obviously T cos theta equals mg. Now, looking at the center, T sine theta is the component of the tension acting horizontally, actually towards the center. And there actually is, you can see here, mr omega squared. This is the centripetal force, mass times acceleration. Okay, and you can see here these two things are actually acting in the same direction as well. So T sine theta is going to equal mr omega squared. So I'll just try and see if I can get this to go. Okay, here we go. So basically, you can see here we've got these forces. We need to resolve that tension T in the light inextensible string. Okay, horizontally and vertically, and we'll hopefully be able to solve some equations when we look at these. Okay, and one great thing is that, in fact, that one great thing which I just stopped a minute ago, that one great thing is that once you've got all these equations, these are the only equations governing the motion, so you'll be able to get what you need from these ones. Okay, so let's have a quick look here. Okay, so resolving vertically. Okay, here we have T cos theta equals mg. Okay. Now, why is that the case? Well, basically, if you go over here, you've got T cos theta acting over this direction, and so mg acting that direction, and there's actually no vertical motion of that particle P. Okay, so it's there's imbalance or equilibrium, if you like, and therefore T cos theta equals mg. That's resolving vertically. Now you're resolving horizontally. Now, if you resolve horizontally, obviously. Okay, the centripetal force is basically acting in the same direction as the, if you like, the tension of the component of the tension T sine theta. I guess you could say it like that. Okay, so those two are balanced as well. Okay, it's an equilibrium. It's not actually moving out, if you like to think of it like that. So basically, it's not moving. It's actually fixed horizontally and vertically. You might actually look like that as well. Okay, so but basically what's this? T sine theta equals mr omega squared. That's the centripetal force. Okay, and that's equal to mv squared on r as well. Okay, using v equals r omega. That's linear velocity equals radius times angular velocity, and you just change that, get an expression for the T sine theta. Also, over here in this triangle here, there's a right angle here at the origin O. So you can use sine theta is what r, the radius, over L. Okay, as well, so you can get that r is equal to L sine theta, and notice, I'll just put a note there that L is actually equal to that length of that light inextensible string, and you can get another expression here, T sine theta equals ml sine theta omega squared, and you'll notice but the sine thetas will cancel and give you an expression here that the tension in the light inextensible string / rod is equal to m L, the length of that light inextensible string, times omega squared. Okay, so tension basically is dependent on the angular velocity, omega squared, you can see here. Okay, let's look at some examples now. Just try. Okay. Well, first of all, I guess some results. I'll go through the results first, then we'll look at some examples. Okay, so what can we get from all of this? Well, if we divide t sine theta by t cos theta, we get obviously tan theta over here. Let's have a look. Tan theta. Now tan theta, as you can see here, is just r omega squared over g. Now that's sometimes quite useful. Okay, you can see that the tangent of the theta is obviously the semi-vertical angle over here, is equal to r omega squared on g. Okay, and if you use that tan theta is also equal to the radius over the height, you can actually get an expression for the height here, g omega squared. Oh, sorry, I should say g over omega squared. You can see that there. And obviously with v equals r omega, or if you like omega equals v on r, you can get an expression for h over here, g r squared on v squared, and you get an expression for v also, eventually taking the square root positive, assuming velocity is positive here. Okay, that's just a measure of speed, isn't it, when we're looking at the linear velocity. Okay, v equals r times the square root of g over h. These are just some results. We're going to use them in the next example. I was a little bit ahead of myself there. Okay, here we are. Alright, let's have a look at this example. Here we have just a quick example. The number of revolutions increases from 20 to 50. Okay, what is the change in the tension and the level of the weight or the bob? Okay, so what's happened? Well, we've obviously changed our angular velocity from 2 pi on 3 radians per second up to 5 pi radians on second. Obviously, we'd expect the tension to increase, and obviously, well, what happens is the bob will start to rise. Okay, so the height will decrease actually. Okay, so let's have a quick look at how we did this. We just basically use this expression here. You can see here. It's okay. T is equal to that one we derived a little bit earlier. ML omega squared, and we just have a look at the okay. We've got m and l, okay, being the same, obviously. That cancel out, and we just look at the omega squared. So here, you can see here the tension is really just dependent really on the angular velocity. So we need to get the angular velocities and divide them by each other. And you can see here we can get, well, what's this, about 6. The tension actually increases by about 6.25 times of the original tension. Okay. Now the height, using g and omega squared, if you look at the basically g over omega squared, again now it's now divided by omega squared, so you can see here that g obviously will be constant. Okay, g being the acceleration due to gravity. Hopefully everyone understands it's 9.8 meters per second, or sometimes people take it as 10 meters per second just for clarity. Okay, now you can't see that 4 pi squared. It's supposed to be squared there. I'll just see if I can move it down a bit. So that it's a bit obscured. There we are. Okay, so basically the height turns out to be 4/25 of the original height. I just marked it in there over there. So okay, so the tension increases and the height decreases. Okay, let's have a look at example 2 now. Okay, let's have a look at example 2. I'll call this one the hanging weight. Well, the weight Q, which is 10 kilograms, is hanging through you can see here, a frictionless ring R. Where's the frictionless ring R? Well, the frictionless ring R is up here. Okay, that's the frictionless ring R. Okay, so it's basically, if you like, you can think of it like the circular motion is actually of the point P. Now, P is over here. P has a weight of 4 kilograms, and actually it's going up. You can see the light inextensible string is going up to R, through R, and hanging down vertically down here to Q, where Q has or is supporting the weight over 10 kilograms. Now the tension is it's an equilibrium. We're assuming the tension in both those sections is the same. Okay, so you can see here it's hanging. Also, if you have a quick look over here, it's the length is 10 meters. It's actually 6 meters below the ring R. The lighter weight moves in a circular horizontal motion. It's the center O here, that red. That's where the center of the circular motion is there. Okay. And it says how many revs are required to support the heavier weight. Okay, so let's have a quick look. So how are we going to do this? How are we going to work out how many revs per minute, if you like, are going to be needed? Well, if we go through the equations, let's actually go through the equations. I think that's the easiest way. I mean, once you've got the equations, they govern the motion, really. And I think this is one of the great things about mechanics, is that once you've got all the equations, you've got all the information. And from that, you should be able to work everything out. Okay, so T equals 10G. Now, why is that the case? Well, if you go over here to Q, the tension in that inextensible string / rod is balanced by the weight here, mg. Okay. Now, obviously, we have to go across over here to P and have a quick look now, and we need to actually look at where is theta. I should have actually theta is actually in here. So I'll get the little pointer to point in here. This is theta. Why would that be theta? Well, the cone's axis and t cos theta are both vertical, hence parallel, and hence that is what they call alternate angle theta in there. Okay, now what have we got to do? Well, we obviously need to resolve the forces. You can see vertically and horizontally, but t cos theta equals 4g. Now vertically. Why is that the case? Well, if you come back over here, t now has to have a component, so t would have a component back across in the vertical direction over here. Okay, it will be going through the angle theta, so it's going to be t cos theta, and that's obviously balanced, if you like, by the weight. It's an equilibrium. Okay, the particle's not rising or falling either. Okay, we're assuming it actually is supporting the weight actually, and it's an equilibrium, if you like. So that's why t cos theta equals 4g. How about t sin theta equals 4r omega squared? Well, we're using that obviously the centripetal force is mr omega squared. The weight's 4 kilograms, and the component over here. Okay, you can see here the component horizontally now of the tension, dropping the tension down horizontally, is t sin theta, and it's balanced by the, if you like, the centripetal force here. So t sin theta equals mr omega squared. Okay, so this is what we'll get here. Now, obviously, we can sub t in because we have t is 10g, so we sub t in into t is equal to 4 cos theta. You can see here, therefore, you can see here the g's will go, and we get an expression for cos theta as 2 and 5. And what else is cos theta? Well, cos theta, if you go back over here to the triangle, you will notice the right angle there. Cos theta is equal to what? Cos theta will be adjacent, which is what? OR, okay, this bit over here. OR, the adjacent side, over the hypotenuse, which is 4. Okay, therefore that must be 2/5 as well. Okay. Well, basically OR, if you like that height above that circle is about, or OR is 1.6 meters. We weren't asked to find that, and I just did this just to show you can find the radius as well, rather about 3.67. Now, we know that t sin theta is equal to 4r omega squared, and we know t is equal to 10g, and basically we can sub in that, okay, well, we know that r is what, 4 sin theta, okay, and you can see here the sin thetas would cancel, and we'll be able to get an expression for omega, and omega turns out to be 10g on 16, the square root thereof, which is roughly about 2.47 radians a second, or about, so it's going pretty quick, 23.6 revolutions per minute. Okay, so basically that particle will need to be traveling at about 23.6 revolutions per minute to support that weight there at Q. Okay. Right, let's have a look at the third example now. The third example is something I'm calling round the outside. So we now have obviously a cone again, and we have basically the particle is traveling around the outside of the cone. Now there's another force here because it's sitting on the exterior surface, the slate edge. You can see there, it's actually at right angles to that surface. Okay, so basically we have this new force. If I'm going to put the particle on the outside, or even on the inside for that matter, it's going to basically, you can see here, it has this new force now coming into play, which is called N, the normal reaction, to the particle on the surface of the cone. Okay, and we're going to basically have a look at a few things. We're going to find the tension in the string, the normal reaction, and also the angular velocity for it to remain on the surface. Now, if I start to increase angular velocity too fast, the particle will actually lift off the surface. And we're just going to now have a quick look at what this looks like. Okay, here we have particle. Let's see if we can. Okay. So it's basically it's got a little cone around the outside. It's sort of like sitting on the exterior of a larger cone. It's actually let's see if I can get it to rotate. Basically, here we go. That's a bit of a tricky one here. I've got all these things moving, but okay, let's see if we can get to it again. It's okay. Here we go. All right, so we have a few more, well, I guess components to worry about here. We've got the normals component. We've got obviously the tension in the lightly inextensible strings component. Okay, we obviously know that the centrifugal force is acting towards the center, so it doesn't have any components vertically. But the other two forces have vertical and horizontal components. Okay, so we're going to have to derive these expressions for the normal and the. Okay, oops. Let's see if I can stop it. It's getting faster. Okay. All right. Okay, so let's go back and have a quick look at how we do this. Okay, so we're basically going to find T, N, and the angular velocity for it to remain on the surface. Okay. All right. Now, how do we do it? Well, we have to basically resolve the forces, as I was saying again. We're going to resolve them horizontally and vertically. I mean, I guess you could also try resolving them tangentially and well, normally, I guess, as well. So you could actually resolve them along the surface of the cone there, the slant edge, and you could also do them normally as well. But I'm going to resolve these vertically and horizontally. Now, if you did that, for instance, you could get components of your centrifugal force if you did it tangentially and normally. Okay, so let's have a look. What's happening? Well, first up, let's go over here. What's equation 1? Equation 1 says that t cos theta plus n sine theta is equal to 3g. Well, where's 3g? 3g is over here at p. How is that possible? Well, t cos theta, actually t, the tension, will have a component across here in the vertical direction, so it's going through the angle theta, so it's t cos theta. N, however, you can see here, is actually acting in the same direction, but it has a component through the complement of the angle. Okay, so it's I should say n sine theta, and that's equal to the weight 3g. Okay, that's not too bad. Okay, how about horizontally? Now, this is an interesting one, horizontally. Well, we've got a component of n coming down through the angle, so we've got n cos, okay, coming down through. We've also got a component of t coming down, acting in the opposite direction, okay, which is t sine theta, going through the complement of the angle, okay. and that is balanced by this centripetal force. Okay, so basically what we do is we say, well, okay, t sine theta minus, it's over here, we just say that, hold on, that the centripetal force is balancing these two forces which are actually in opposite directions. So basically it's not moving out at the moment, it's in equilibrium, so I guess you could say it's resting on the surface at this stage. Okay, so we're assuming that the angular velocity is small enough for it to rest on the surface. We'll see later that you have what's called a boundary value for omega, which basically makes it stay on the surface or escape from the surface. Okay, so now what else do we do? Well, first up, let's have a look. I'll just try and move this down here. We have that sine theta is r on 4. We can sub in r as 4 sine theta. Okay, that will give us that t sine theta minus n cos theta is 12 sine theta omega squared. This becomes equation 2. Now, how do we solve this for t and n? Well, you can see here we've got t cos and t sine, so we need to multiply 1 by cos and 1 by sine, obviously to eliminate either of them, so depending on which way you go. So if you do 1 by cos and 2 by sine, you end up getting t sine squared plus cos squared, which we know hopefully is 1. That gives us this result here, that we've got the tension now in red. Here, the tension is, this is what the tension is. Now it's 12 sine squared theta omega squared plus 3g cos theta g, obviously gravity. Okay, omega, we don't know what it is at the moment. Okay, so but we're assuming it's less than the optimal or escape omega, if you like to think of it like that. Now if we do the other one, we get 1 by sine now and 2 by cos. We can basically eliminate t and solve for n, and we end up getting here, you can see here, n is equal to 3g sine theta minus 12 sine theta cos theta omega squared. Some people combine that into the 2 theta results, but that's all right. Okay, now, so what happens? Well, when it leaves the surface, okay, I think this is the easiest way to do it. Just say, look, well, hold on, there's no n anymore if it's going to leave the surface. So there is if n is actually equal to 0, this will give us our boundary omega, or our boundary angular velocity, which is right here, c. It's the square root of g over 4 cos theta. Now, obviously, omega would need to be less than that if it's going to stay on the surface, and greater than that if it's going to leave the surface. Okay, so, well, that's all there is for today. This is a fairly long video, so bye for now, and we're going on to bank curves on the next videos. Okay, bye for now.